computational and mathematical tools a more quantitative, theoretical point of view. All right. Oh, it's all there? Okay, I'll try. So the volume is now the highest. Any better? Yes. All right. So these are the different brain of different mammals. It's all mammalian brains. You put them together. This diagram, the human brain is here, very big, so we're very all very familiar with. There are also other smaller brains. Like a macaque monkey is one brain that people have used a lot in system neuroscience research. There are also like smaller brains, like this. Human actually does not have the largest brain. Right? This is a human brain in comparison with a whale. Whale would be much bigger. These are pretty smallest brain of mammals. It's smaller than a mouse, smaller than a rat. It's not smaller. So this is a diagram that shows the brain of different animals. Compare the brain weight against plot the brain weight against the body weight. So basically, you see is that of course the larger animals have a larger brain, tend to have a larger brain. They're human here, yeah, human here. A little bit larger than usual, but not extra much. There's some larger animal, like a whale has a bigger brain, but their body is much bigger. The idea is that if you have a bigger body and more muscles, and your body is big, your exercise will go a long distance to connect with other parts of your body. Then you need a big cell to power up all your big exercise. So that's what you would expect. But those kind of curves, when you take a look, it's not very tight. I won't say they're correlated, but you see there are lots of difference. Right? And also, you see here, this is a logarithmic scale. The distance between two bars here is 10 times. So the deviation like this, many times, deviation from the regression line. So there was lots of. So if you look at, because this is sort of expected, because the body weight and their brain is not directly correlated. You can, big gain in body weight, you want to eat a lot, play a movie, for example, but your brain size is still the same. So this correlation is not expected to be very tight. But if you look at the brain itself, the different parts of the brain, the relationship is much more precise. I'll just give you show you a few examples. So this is a human brain. So first of all, when you look at this, what are all those areas? All neocortex, right? So for all the mammalian brain, if you only say there's one thing, why is the brain of mammals different from all the other animals? The number one, the biggest difference is the cortex, the neocortex. We haven't learned this in other lectures, I suppose. So what's the neocortex? Well, for the human brain like this, pretty much everything you see here is a neocortex, is what the cortex. All the convoluted stuff. The only thing that's not the cortex in this diagram, only this little thing here. This is what you have learned this, right? This is a cerebellum, and this is a small brain. And this part of the brainstem, and maybe part of the spinal cord. Only these things are not the cortex. Everything else you see is a neocortex. So about 80% of the human brain, the volume is all occupied by this convoluted thing. This is actually a single sheet of cells. Actually, the two sheets of cells on the left side and the right-hand side. They are folded, but actually, topologically, it's a continuous sheet of cells. They basically put on top of all the brainstem stuff, right? So compare with non-mammals, like reptiles or birds, different that all those animals don't have this big thing here, the neocortex. So the neocortex is a major innovation for the mammalian brain. And it is very big, getting big, very big in human in fact. the brain finds a trick in here. You can use this many, many times to do different kinds of things. When you see a diagram like this, I'm sure you have seen many, diagram like this with colors. Say, oh, this is a language area, that's some kind of motor area. It's basically correct. It's very specialized. So you look at cortex like this. If I say in a very stereotypical, very simplified view, it's like basically the back of the brain, like from here to here, the back. If you cut the brain in half, the back half of the cortex is pretty much sensory. For example, the visual system is here, right? So the sensory is here. The auditory system, auditory input is here. Right? So this is mostly sensory. The front part, okay, this big chunk here, is like motor control and other planning and more higher level functions. So this is sensory and motor system. That's the most basic thing we can do. All right, so this diagram is many different animals compare different brain parts. Some of the neocortex is a big thing here. So each dot is one animal species. They compare the different parts against the whole brain side. Of course, the neocortex is more. I think this diagram is they have offset. So if you put everything together, it overlaps. So that means they have plus some things. So each of the brain structure, they added some numbers to make the different lines and not intersecting each other. You can see correct. But I show you, I just want to say that across many different animals, you can compare different parts. The neocortex, right? That's the big part of the brain. There are two major actual structures in the neocortex. One is called striatum, which is the basal ganglia. You know that, right? Another is the cerebellum, as I mentioned. But that you cannot see. It's actually between the thalamus and the cortex. Somewhat just buried inside. This is two major parts. Diastema, the cerebellum. This is the thalamus. They have different names. That's not important for now. But I want to use this to show you that when the animal, different size animal, you can compare different brain parts, all the major parts here. The name actually doesn't matter for my lecture, but I think this gives you an impression that when the brain grows bigger, all different parts all become bigger. It's not just only neocortex bigger, but you can see the slope when the neocortex increases faster, the slope is a little bit higher, and when the brain size increases, this neocortex increases a little faster, but everything increases. The whole thing scales up, put at a different speed. So what's the relationship? There are some studies, like this one is one from Stevens, just shows this part of the thalamus. When you learn the visual system, you remember the neocortex. This is like for V1, the primary visual cortex. The number of cells in the primary visual cortex compare with the number of cells in part of the thalamus, the lateral genicular nuclei. You haven't learned that in your visual lecture. Okay, so the vision signal from the retina, you go to where? The first step is always in the thalamus. All your sensory system, with the only exception of your olfactory system, the signal goes to part of the thalamus. Thalamus basically sit on top of your brainstem. Spinal cord all the way goes out to the brainstem. On top of the brainstem is called the thalamus. And that's a gateway to the cortex. The cortex is everything that is surrounded, everything, the big stuff on the top. So the thalamus for the visual system is called the lateral genicular nuclei. That's the final gateway to the cortex. So this diagram shows that each dot is different animal species. So for different animal, there's a very precise relationship. Actually, the number of cells in the cortex compared with the brainstem and the thalamus, they have it's a power law relationship. Right? This is so basically, the number of cells in the cortex end is proportional to the 2/3 of power. What is called? 3/2 of power. So there's something like a power relationship. So this kind of stuff you have seen. I'm not going to argue why the theoretical argument this would be true. I'm not sure this argument is correct or not, but there are many laws have been discovered about this. So different parts of the brain, when they grow up, you have a bigger or smaller one, they have this kind of precise relationship, for some reason. It's not when you say the brain is very messy, it doesn't have anything. It's not like that. So their relationship, but we don't understand it. That's really better way to say it. give you another example. It's called the green matter versus the white matter. So given this brain slices, you see all the cortex, all the convoluted stuff, right? It's continuous, topologically continuous. So whether you were outside or inside actually doesn't matter. It's really the connection of this cell to other cell that matters. So this is topologically to save space to fold this off. It's really the location, whether you're inside or outside, actually doesn't matter. It's based on what I'm understanding now. So you look at these things, you notice, so all these dark area, that's the cell bodies of the neurons. And all the white thing inside, that's the axons. So you already learned what's your axon, cell body, and dendrite, right? Yeah. So basically, the axon, for a neuron, you know the brain is made of neurons, right? A neuron is processing information. Now that's your heart is like a pump. It pumps in. Blood goes in, blood goes out. We have the low pressure, even high pressure blood. Your gut and the food goes in, and waste goes out. There's something, there are input output. So the brain is made of neurons. What's the input to a neuron? Information goes through the dendrite, right? And what's the output? The output is activity on the axon. The axon is just output of the brain. So all the white things is white matter, and here is all the axons, this output of the neurons. So you look at the mouse brain, or a rat brain, rodent. So their cortex is very smooth. It doesn't have convolution because the total area of the cortex is very small. There's really no need to fold that thing because it's so small. It makes it continuous. So the fibers, it's only this white thing, very thin layer right here. Not many. So here's a way to look at the brain, all right? Instead of which you label different parts, they have different function, label different color, but if you really look at the brain, so the right way to look at the brain is by a method pioneered by Cajal, the Spanish anatomist, right? He basically used a method, a gorgeous staining method, to see the whole cell, and then he looked at different brains. And here's actually one drawing by Cajal for a baby kitten, I think. It's smaller, and this shows you what the brain really made of. The brain is made of neurons, right? We just said. And neuron is just one type of cell. But if you compare a neuron with any other cell in your body, what's the most striking difference? One thing is, okay, a neuron is excitable, but your muscle is not excitable, right? It has electric signals. But I think what's strange about the brain, about the neuron, you can see with your eye is the morphology. Right, it is. Is there a question here? Yeah, the axon, yeah. The axon is very strange. The dendrite is already strange, but it's not that big. The axon is really long. And I think that's one of the things that's so unusual about the brain, about the cell. So this is cell body, right? Of a cell in the cortex. The pyramid leaves the tree-like structure, the dendrite, is the input to the brain. The output, of course, is single dendrite. One thing interesting is that a neuron has many inputs. A typical cell in the cortex receives thousands or tens of thousands of inputs from other neurons, but there's only one output. There's only one axon. Very typical. The axon may bifurcate, branching, and you reach your destination. But that's just copies of the same signal. It's just only one output. So that white matter on the fiber of those things here are basically bundles of axons. So the size of the axon, how long it is as large as your whole brain. For example, the neuron on this right side of the brain, it projects this axon. If you go to the white matter, it can go all the way across the brain, go to the other side of your brain. So that's a single cell. Do you know how other cells, it's like this big? Usually a cell you cannot see by your eyes. And this cell must be, as wide as your brain. Let's go from this side to the other side. It's not really. It's big only in one dimension. It's very long. The thickness axon is not that big. Right? You cannot see it. It's too narrow. But its length is really remarkable. You see, why it has this very strange morphology? Well, that's very distinctive. There's no other parts of your body like this, right? That's because the neuron want to send a signal to other parts of the brain, right? Send to other neurons. And what kind of signals goes on the axon? You have learned this. What is that signal? Well, that's actually something very elegantly simple in the brain. It's just only one signal. It's action potential, right? It's only one. If the neuron in one part of the brain want to talk to other parts, a neuron in a different part of the brain, on a fast time scale, I'm talking about in a fraction of a second, there's only one way you can send a signal. It's that action potential. If you want to send a signal in a longer way, maybe there's some chemical signal that's much slower. It's not at this time scale. The fast time scale, there's only one signal. So that action potential. The action potential you have to learn is all or none, right? So either you have one or don't have one. So the signal can be what? Because the shape of the action potential and how it changes in time is stereotypical. It's always the same. So the only way you can send the information is time. The timing of the action potential. That's the only way you can signal. You say, oh, that doesn't matter because there's so many other ways to signal. No, it's not. Your brain activity is only, neuron is actually everything. That's right. You don't have anything other than just neurons interacting with one another. And so that's very significant. The neuron can send a signal only in one way. There's only one kind of signal. It's the timing of the action potential. All right. So there's a very interesting relationship between the cortex, the gray matter. Gray matter is basically, you look at here, it's simple, right? You look at this here, people say, oh yeah, this is a part that have a different name, a label, different things. But you look at Kahal drawing, you see more clearly, it's just a bunch of neurons, right? So this gray matter is basically the cortex, basically made of the cell body and the dendrites, all the neurons. The white matter is just axons, the long distance axons, right? When you look at it here, you can see it, right? These are the fibers of axons. All the shells, all the cell bodies that do local information processing. Oh, these are the wires that send signal to a long distance, basically. That's a basic organization. So this is the removed part of the gray matter. You can see all the fiber that go all the way from here to different parts. It's so interesting when you think about this. It's really all made of single cell. It's that long, right? Yeah, I got this online. There's someone, this is a real person. Somehow they got their brain and the spinal cord, sort of like a sci-fi movie, horror movie or something. But one thing is interesting. You think about this. Like, this is for the nerve in the arms. When you move your fingertips, you all know your muscle contracts because it receives input to the synapse, right? It's the acetylcholine released, we make your finger move. But where is the motor neuron actually located? The motor neuron have activity. The action potential travel down the long axon. The nerves go all the way to your muscle on your fingertip. Where is the location of that motor neuron? You know? Yeah, it's in the spinal cord. It's here. So you see this neuron is actually sitting in here. Its send axon that long, as long as your arm go all the way to the tip of your finger to make movement. So that's a single cell. It's really long, right? Yeah, this is just like when the animal's brain become bigger, you need more wires because you need to go a longer distance to other places. So you're not just proportional, actually you're longer. Yeah.
So I know you were saying, so the axons are in the white matter and the cell bodies are in the gray matter, but do signals travel from inside to out or from out to in?
Oh yeah. The axon your signal goes in only one way. It just goes. Because axon, I said, this is the output of the neuron. The neuron is activated, it goes along the axon, starting from the cell body, they go along the way. Okay. Yeah, so maybe you learn this, the axon itself, the structure of axon itself, you can go both ways. Just like the highway, right? Our highway here, you can drive both ways, right? There's no physical limit, right? If there's, you know, in a sci-fi movie, there's only one person driving on the car, you can drive any direction, right? This is because you cannot get out because it's a social convection, you should go this way, but not the other way, right? But now, inherently, the highway itself, it doesn't block you, you can go the other way. So the axons are like that, they can travel both ways. But in reality, they travel only in one way because the signal always comes from the cell by the input to the dendrites. Then the cell make a decision, fire action potential or not, and that signal go, because you start from there to go only in that way, right? Just like a highway, once this entrance, you can go only go in that way. Yeah, so it is the way where signal originates, and not the structure that makes it only move in one direction. Yeah, but in experimental setting, people can do that. They can do retro anti-dramic activation. I can stimulate somewhere, the signal can go backwards. They can do collision experiment, do stuff. They can try to check whether the things are connected or not. But you can use that in that way. But in reality, they only go in one way. So you see, only the brain is very complicated, but some of the structure is very extremely simple and uniform, right? I think the fact that it's made of a neuron is a very uniform feature as across all animals. How neurons are activated by basically the same mechanism. As I'm going to get in there in a moment. So you look at this, it's also a very nice relationship. This is a gray matter volume on this direction. This is on logarithm scale. This is a matter volume of white matter, is all the axons on the log scale. You get a straight line. So basically means this is a power law. The white matter proportional to gray matter raised to power actually greater than 1. That means if you want to build a larger brain, or you want to build a faster computer, you know, how do you scale up your components? Well, because the cortex kind of similar, even you add more stuff, you make a bigger brain, you need disproportionately more wirings for the long distance wiring. Yeah, that's what it says here to you. But this one has more animals, so you see the relationship pretty tight, right? So this is a gray matter volume. This is I mean, how many? This is the 1, 2, 3, several order of magnitude, like 5 or 6 order magnitude, right? They go that way. This has this sort of very precise relationship. So I just, okay, before I go into the Hodgkin-Huxley theory, I'm sure you learned before about this neural activation, I just a little bit more about anatomy, right? Say how uniform the cortex is. Although the cortex is different, I'm sure you see pictures of why different parts of the cortex are actually different. There are differences, but there are also uniformity. And I want to emphasize uniformity here. So this is the cortex of different animals, right? The bigger animals have a thicker cortex. Gets thicker when the brain gets bigger, as it shows here. But there is a uniform relationship, which means that for different animals, right? This is the compare a human against a mouse. The cortex gets thicker. But the total number of cells under a uniform area of that cortical column, right? Just you have a column perpendicular to the surface of your cortex. Cortex has big sheets, as I said. You cut into a small column. The total number of cells is about 10 to the power of 5. It's like 100,000. About 100,000 neurons per square millimeter. Yeah, that's the area. This is about the same across all different animals. So that suggests always to people, maybe the cortex, to find some tricks, they do things that basically the same way. You have a bigger brain because your axon needs to go a longer distance because you're just, like the city is too big, your highway system has to be bigger. But the number of processing units of different neuron, maybe different animal, actually maybe the same, right? So actually the same. So there are like great uniformity. Maybe there is exception for the visual cortex. Because the visual cortex, you have many more cells. You see here, but that's not because the neuron that send axon to the other part of the brain has more. Actually, it's about the same. It's where they increase the local cell. Because the striatal cells is sort of very small cell, but those cells their axons don't go out to the white matter to other part of the brain. They only do something local, like a processing. So that shows for the primates, like monkey, the humans, we are very, very visual animals, right? Half of the brain is actually related to the visual function. We're very, very visual. So this is a hard working part of the brain, so they have more cells, develop many local cells to do the local processing. So these are just very, very crude, very quick overview of some aspect of the brain anatomy. I just want to show you that there's, even the brain is very complex structure, there are also some facts very, very universal, right, across different brains. Yeah, this shows the neocortex. Once again, the different cells. People always try to figure out what's the circuitry, what's the basic circuitry. There are different cell types, right? Are they connected with some motif or some kind of maybe some repeatable structures? Maybe there are some, just like if you design electric circuits, there are some little standard tricks. How do you amplify things, right? How do you see the difference? Maybe there are some maybe standard ways. And this part, I'm going to talk about a few possible ways bring me to some computation. But it's fair to say, so far we haven't figured that out, right? I think the most solid theory we have so far is basically only the how an individual neuron works. That part is very clear. But how different neurons wire up to form a network, to form a circuitry, how to use that to do useful computation. Our knowledge is very limited. But there are a few examples extremely interesting. So I'm going to show you in my future lectures. All right. So the only animal we really have some knowledge about this, how the things that connect with each other, is this C. elegans. Right? It's a free living worms. We have I think a 300 and a 2 cell actually neuron cell. The whole body have like less than 1,000 cells, I believe, right? So 900 some cells. 302 cells are actually neurons in this animal. So this is the only animal that's how the different cells connect with each other is known. So each other cell identify, you see how each cell connect with each other is based on anatomy. People make the slices and then use electronic microscope and then reconstruct the three-dimensional structure. For this animal, so one thing you look at this nervous system that's plotted here. The first thing you think, it doesn't look like a neuron. A neuron in your mind, of course, we always see the neuron like a tree-like structure, like a tree. But here, where is the tree? What's the cell body? Where is the axon? Well, in this case, it looks like sticks. Look at stick. This is because this animal doesn't have so many neurons. Each cell is not connect with so many neurons, only a few, right? You really don't need that tree. The tree is because you need to expand your area of your surface of your neurons, so you want to connect with many other neurons. But here there's only a few connections, you really don't need that. So it looks like a stick. Doesn't look like a neuron. But this is the animal. The connections are all very clear. So this, you can see how these cells connect with other cells. Right? The cells only receive inputs from outside. These are the sensory neurons. Right? And the neuron, it doesn't send out the neuron at the other end would be motor neuron. Receive input to drive muscles. Right? They only have output. That's the motor neuron. You can figure out. And many other neurons. So the connectivity. This is they have a 302 neurons. The entire connection matrix has been worked out. Right? This is on this side. This is a neuron from 1 to 300 something. This on the other side. This is a connection from any neuron to any other neuron. Right? On the diagonal line would be self-connection. You connect with yourself now. So this is the only animal you can see the entire structure of the nervous system. Right? From other animals. Only the vertebrate, like this is an animal we use a lot, aplysia. You see the ganglia, this nerve is made of ganglia. It doesn't really have a brain, right? But those animals, their cells, you can be compared across different animals because their structure is basically the same. If you open up this ganglia, you say, oh, this cell, you can have a name for each of the cell. You have a different animal, you still can find the same cell. It's really the animal, the cell by cell is actually the same.
So for these kind of animal, like say, like these, the connection, you compare different animals, they're identical, right? Whether the two neurons are connect with each other or not, it's genetically determined. So, but only how strong the connection, that may depend on the experience. So those animals, they are sort of pretty much hardwired. For like a human like this, we sort of just like a fish or a more complex animal, it's no longer true. Yeah.
Why isn't it symmetric about the same?
It's not exactly symmetric. It's roughly, yeah. It's not exactly symmetric, right? So actually, it's good. You have a good eye to see the symmetry. So we talk about a theory of memory, like a half-wave network. It turns out whether connection is symmetric or not, it's whether two neurons they reciprocally connect. If I excite you, you excite me, right? If you reciprocally connect, that will be exactly symmetric. This connection is not exactly symmetric, but they tend to be. If you excite me, I excite you. So, right? It's basically just like a gang, right? They excite each other. The whole group excites you. No, if you love me, just like that tend to be true, and there's also theory behind that, but not exactly true, right? Because some neurons is inhibitory. Some inhibitory neurons inhibit each other. Sometimes you excite me, actually I inhibit you, right? They're not exactly symmetric. Sometimes you have like a hierarchical structure. After you learn anatomy of the brain, like a cerebellum or basal ganglia, if you learn that, you see some of the connections just only goes one way, they don't go back. So you cannot have reciprocal connection. But the reciprocal connection is a very interesting topic. I will go back in my future lectures. It has very strong implication for the dynamical stability of memory. It turns out it's a crucial condition, actually. For animal like this, very complex animal, the total number of cells is not conserved. Human, if a different individual, the number of cells are different, right? So you identify the same cells, see all they connect the same way. It doesn't make any sense, right? Because we don't have the same number of neurons. But we do see that, here at least some facts. So that 98% axon white matter interconnect different area of the neocortex itself, rather connect with other parts of the brain. So what this means that only 2% of the brain is actually is connected with reality, right? Your motor system signal has to go out. Your sensory system, your vision, has to go into your brain. And those axons are only a very tiny fraction of all the connection inside the brain. You look at this, all these wires here, 98%, that's the vast majority, connect to different parts of the cortex, talking to each other, right? Not talking to you. Maybe when you're dreaming, maybe that's what generates some activity in your brain. But the sensory signals and your motor signals, your command, and all those things is only within that 2% of all the connections, very tiny. All right. So for the theory of the brain, all right, let's go to so how does brain work? What's the current understanding of how brain works? What's from a theoretical, mathematical point of view? I think the foundation, of course, is Hutchins-Huxley equation. I think you already learned this when you study the cardiovascular system, right? Yeah. I think this is classical biophysics. It shows how individual neuron works. But it's a piece of the membrane works, right? But actually, this is all the way we understand how a neuron works, basically based on similar kind of theory. So when you look at the equation, right? So why this equation is valid? Well, look at the first one. The capacitance and the voltage time derivative equal to all the current. So this equation is not really a neural equation, right? It's true for everything. If you have a RC circuitry, it's like you have a capacitor, a resistor, you connect it together, and you have an equation like this, right? This is true for all electric systems, right? With a resistor and capacitor. It's not specific for the brain. So if you write a different current of like sodium, calcium, you get this conductance, this difference of the voltage relative to some equilibrium potential. These are just Ohm's law, not just specific for the brain. And equilibrium potential, these are for the Ernst equation, right? That's true for any, if any membrane that some particle cannot pass through freely, they have a gradient of concentration, you have equation like this. It's not only true for the brain, if you make a, it's true in many different cases, right? Even for like semiconductor, rather you do have this kind of equations, right? So what's so special about the nervous system? That what's specific for the nervous system part of those stuff like this rate functions. You have learned this. I don't bore you with the detail of these. These is really specifically describe how that piece of squid axon actually works. Right? And these things, when you look at this equation, are kind of ugly, right? So what are these form? Why exactly is this number? Where do those things come from? Nobody, I'm sure nobody has said why this has to work this way. We don't have a there are actually theories of how this ion channel works, how the protein changes form, and how the ion channel works. That's more complicated. But these are not derived from first principle. It's a fit to the data. It's just like an empirical equation. And these are really specific to the nervous system. So basically that's how this Hodgkin equation holds. Some part of it is true for pretty much all the system, and these are specific for these things. For these things, it's not hard to see. You know the system has it generates action potential like this, right? That the membrane potential, it can if you don't do anything, it has a resting potential, it stays there, and then it can be activated if you have a threshold or the current strong enough. You have action potential. That should last only maybe here it's 0.5 milliseconds. So basically the time scale is that the width of action potential about 1 millisecond, right? So that already gives you upper limit, so how fast you can send the signal in the brain. So now based on this fact, you already know the speed limit of your brain. So when you have a computer or your cell phone, so what's the clock speed of your CPU, right? Your computer. You know it's in usually it's some 1 gigahertz, 3 gigahertz. It's in the range of gigahertz, right? That's like 1 billion hertz, is that right? 10 to the power of 9 hertz, right? In the human brain, so let's say you send signal by action potential, right? When you send the second signal, you have to wait for a while because there's a refractory period. There's no way you can send a signal like 1,000 spikes per second. Action potential is called spike. The 1,000 spike per second, because the width is already about 1 millisecond. You cannot pack 1,000 of them together. So the speed limit of the brain is just a few hundred hertz, a few hundred action potential per second. You cannot go faster than that. So that's much slower than the clocks of your computer. Your computer is 10 to the power of 9, right? This is the power, 10 to the power of 2. Right? It's like order of magnitude difference, much slower. But the brain is still more powerful for many things. Another is how fast is the speed of your conduction. In the past, people saw the speed might be very fast. Right? The actual measurement is by from Helmholtz. Helmholtz is the same Helmholtz energy. He found out the brain speed actually is much slower. The fastest speed about 100 meters per second. 100 meters per second, so pretty fast, but it's not that fast. Right? So here is plotted the conduction speed as the diameter of the axon, right? So there are two different kinds of axons. So basically, when the diameter is thicker, the speed is also faster, right? There are two different major classes. The slope is different. So one is sort of the velocity, the conduction speed is proportional, roughly proportional to the diameter axon. Those are sort of magnetic axons. The axons have an insulation. still working. So some unmanaged axon, just a bare axon. So bare axon, the conduction, it all increases with the thickness of the axon. Managed axon is sort of proportional to that. That's another major innovation, right? Because for the squid axon, the giant squid, and where is this? Squid giant here, see? So there's really thick. It's almost, this is 1,000 micron. This is 1 millimeter. It's really, your eyes can see it, they're pretty thick. Because you want to escape, right? You have to be very fast. Otherwise, if you're too slow, you may not survive. And so to make that fast, you have to make it very thick. But if you compare the squid axon, compare it with like a frog, like a vertebrate animal, that's a major for motor reasons, they have managed axons. You see, they can have the same speed, right? But the thickness is only like a 4 micron. 4 micron is how much? It's like the size of your red blood cell, much smaller. Instead of 1 millimeter, it's gigantic. All right. So just based on single fact, let's look at this. Is the I got from the website. A lot of like maybe the scientific program, scientific TV shows, people usually see some diagram like this, right? So there's a neuron. There's some like electric signal zapping around. There's some signal going around the brain. Right? Sometimes even show that's like multiple, like repeated spikes traveling around the neuron. What's wrong with this picture? Of course, this doesn't have a, I'm not sure which is dendrite, which is axon. They just don't, they probably don't understand the difference, but that's one problem. Another problem is that how wide do you think is the spike? If a neuron is activated, the action potential travel along axon. That's a standard, model for the understanding how the brain works. What's the width of this activity? This is sort of like a snapshot of a traveling wave at that moment in time, right? Well, based on this, we can do an estimate. So based on this, let's suppose the spike is 1 millisecond wide. The speed is 100 meters per second, right? So this width would be like a 0.1 millimeter. It's like a 10 millimeters. It's like this big, right? About the width of, about the distance between your two eyes. If a wave traveling at 100 meters per second, right? If it's 1 millisecond wide, it's about 10 centimeters. Right? It's about the width between your two eyes. So even if you were like 1 meter per second, that's just only 100 times smaller, right? That still would be, how much would be 0.1 millimeter, right? Is that right? Oh, it's about 1 millimeter, right? 1 millimeter is pretty big. Compared with things like this, this is only like 40 micron or something. That's much smaller. So there's no way it would be like this. It's much bigger, out of scale. It's not. So the width of that traveling wave would be much bigger than the entire screen of this stuff. And several of the materials are larger. Right? There is no way you see things like this. This is utterly impossible. Right? So for the fast activity from one side of your brain to the other side, it's just almost that wave will span the entire length of the brain. So that's one action potential. It's very wide. Right? It's not like this. This is totally wrong. Right? All right, in the last few minutes, I just, in my next lecture, I will show you more mathematical equations, right? But now I'll just show you it's very intuitive, but it's some interesting that just based on the signal traveling along the axon, that can do what a dendrite. You can do useful computation just based on this. I just said, because if the signal is stereotypical, the only signal you really can send is time, right? So how can that be useful? I'll give you two well-established examples. One is how you detect motion direction. Let's suppose you have a neuron here, right? You have two different dendrites. One is longer than the other. Suppose you have a sensor. So suppose there's some small thing moving. You first excite some sensors here that go down the signal to here. And later you cite something here, the signal goes down here. Let's just assume this neuron is activated only with the signal, the two source signal arrive at the same time. So strong enough, right? If only one source is not strong enough, just assume that, all right? So this is the first, this is a basic idea for this type of model, is that how you detect whether something is moving toward to the right or to the left. This is because this conduction presumably is slower, this is a faster, right? So only if this signal from here had a head start, and then you can, just the signal arrived right here. Only we have a certain range of speed, right, in the correct direction. If it goes in the opposite direction, signal from here as outstart, but this is a short road, right? This will arrive earlier. Well, it's not strong enough to excite the cell by our assumption. So this case, neuron will not be excited. So whenever the neuron is excited, it means the thing must be moving towards the right at a certain range of speed, right? So this is sort of, you use a time delay can do this kind of detection, and the threshold. Right? This is one very early example. There are evidence that there are some asymmetry in the connection. In different animals, it's probably true, but so that's a very early example. This work can be done. Another example is very interesting. How you detect intraoral time delay? Well, we all know that left and right, the sound signal go to your ear at a different time, but that time is very tiny, right? Say, human ear, if I click on your left or on your right, what's the time? One signal will arrive in your ear at a different time, but how much is the time difference? The sound signal is about 300 meters per second. Right? Your head is like less than 20 centimeters. Right? So the time, that means the difference of time is less than 1 millisecond. Right? Less than 1 millisecond, that means it's smaller even than the width of your action potential. Right? So that's pretty remarkable. You can detect that, right? That's even your basic, when you say the basic signal is that action potential, it will take about 1 millisecond. And you can detect time difference even more narrow than that, right? Very reliably. How can that be done? So here are the models proposed a long time ago, in 1940s, a very long time ago. So the idea is that you have axon from your left ear, and they send different branches to the bunch of detectors at different spatial locations. So that means the idea is that you actually, when this signal from your left ear goes, it first drives this cell and drives that and drives that at a different time. From your right ear, the signal go in the opposite direction. All right. So if the both signal from both sides, suppose, start at the same time, if that's the case, in this design, the two signals actually meet in the middle, right? In all the other cases, one will arrive earlier than the other, so they won't exactly match. So that means if the cell has a threshold, only both signals are active at the same time, you can drive the cell, only this cell will be activated, right in the middle. So if you say the sound signal is close to your right ear signal has a head start, right? Then when the left signal from the left ear comes, they will match at a different location. So basically you have the detectors, depending on which cell is activated, along this line, it will have a map, so where is that azimuth direction in the environment. That's a pretty clever model, right? And this is probably true. This is based on the anatomy. It's in the bind owl. In some area that's presumably it detected intraoral in a time delay. They just have this structure. You see this axon goes here, have the branching out in a different location, and in the other side of the brain, it goes in the opposite direction. So they have some anatomical evidence, and even have some physiological evidence. This might be actually work. So that's this is just a very simple example that shows even that little time delay, you can use that to do some useful computation. So in my next lecture, so this is all for today. Next lecture, I'm going to talk about when you have a synapse, you put things together, you can do things much more powerfully, sometimes in a surprising way. All right. So that's all. Thank you.